Welcome to this explainer. Okay, so today we're tackling something absolutely massive. We are going to explore the fascinating and honestly highly debated relationship between entropy, physics, and the ultimate origins of biological complexity. If you've ever found yourself wondering whether natural processes alone can actually explain the intricate machinery of life, especially in a universe that seems to be constantly running out of steam, you are in exactly the right place. Let's get into it.
Here is how we're going to break this down today. We'll start with what is the second law, then look at Earth as an open system, move into order versus specified complexity, touch on time's arrow and heat death, and wrap the whole thing up with the limits of physics. All right, section 1, what is the second law?
So, you know how people casually toss around the word entropy to just mean chaos or a messy room? Well, in physics, it's actually a lot more precise than that. It's a measure of the number of microstates that correspond to a macrostate. In plain English, it describes how energy naturally disperses in a closed, isolated system over time. It's basically the universe's natural, built-in tendency to spread energy out rather than keeping it nicely concentrated. To put that in everyday terms, natural processes always trend toward equilibrium. Left completely to its own devices, energy just spreads out. Heat always flows from a hot object, like your morning coffee, to the cold room, right? Never the other way around. This dictates that the universe itself is constantly running down toward maximum entropy. It's heading toward a perfectly balanced, energy-exhausted state that physicists often call heat death.
Which brings us to section 2, Earth as an open system.
Now, you will hear this claim quite a bit in origins debates, that the law of entropy outright disproves evolution. The thinking goes, hey, life is highly ordered, and the universe trends toward disorder, so biology has to be violating physics, right? We really need to tackle this fundamental question head-on. Does biological change actually violate thermodynamics? Well, the short answer from the scientific community is no, it doesn't. And the reason comes down to this absolutely mind-boggling number: 10 to the 17th power watts. That is the amount of solar energy continuously bombarding our planet from the sun. Earth is an open system. We aren't trapped in a closed box. We are literally plugged into a massive, continuous cosmic power source. Because of this incredible influx of energy, local decreases in entropy are perfectly permissible. This is scientifically settled and totally consistent with the second law. I mean, energy flow can absolutely produce order, and we see it all the time in nature. When winter rolls around, water freezes into beautifully ordered snowflakes. Crystals grow deep in caves. Convection cells organize themselves. All of this is allowed by thermodynamics, provided that the global entropy of the larger system, the whole universe, keeps increasing. Moving on to section 3, order versus specified complexity. Here's where things get super interesting. We need to draw a really sharp line between two concepts. On one side, you've got simple order, like that snowflake we just talked about. It naturally grows into a pattern form driven by the fixed, rigid physical laws of molecular bonding, but it contains no actual instructions. Contrast that with living cells, which exhibit what's called specified complexity. They require massive functional integration and digitally encoded algorithmic instructions. It's literally like computer software. So this highlights a massive distinction in the debate: permissibility versus sufficiency. Look, just because the physics of an open system permits biological complexity, that doesn't automatically mean energy flow alone is sufficient to actually create it. Think of it like this. You can shine massive amounts of sunlight onto a pile of sand, but it's never going to spontaneously turn into a silicon computer chip. Raw energy is necessary for sure, but without some kind of organizing principle or intervention, it's just not self-sufficient. Now, researchers studying non-equilibrium thermodynamics will be quick to point out that energy gradients can create some amazing self-organizing patterns, things like chemical oscillations or heat-driven Bénard convection cells. But there are categorical limits here. These self-organizing systems rigidly follow fixed physical laws. They absolutely do not encode symbolic information, and they do not replicate with variation. There's a universe of difference between a neat crystal pattern and an actual algorithmic instruction set. To get the emergence of true genetic coding, you need elements that thermodynamics simply doesn't explain. Biological code requires symbol-to-function mapping, robust error correction, and incredibly complex translation machinery. The whole shebang. These are the undeniable hallmarks of a genuine communication system. The second law of thermodynamics certainly doesn't forbid these systems from existing, but it also completely leaves open the question of how they originated in the first place. Let's zoom out a bit for section 4.
time's arrow and heat death.
The second law acts like a strict one-way street sign for time. It actually proves our universe is not eternal. Think about it. If entropy has always been increasing, it couldn't have been doing so forever, or we'd already be completely out of usable energy. So this points us to a finite past, a beginning with remarkably low entropy, and a future that is actively trending toward an energy-exhausted state of cosmic heat death, where stars eventually burn through their nuclear fuel and galaxies just dim out.
And because systems naturally decay without input, this arrow of time means macroscopic physical processes are entirely irreversible. You see this in your own kitchen. You can scramble an egg, but no matter how hard you try, you are never, ever unscrambling it back into the shell. On a cosmic scale, stars burn hydrogen, but they don't spontaneously run nuclear fusion in reverse. Time moves in exactly one direction, toward greater dispersal of energy. Which brings us to our final part, Section 5, the limits of physics. So we know from physics, specifically through something called Landauer's principle, that processing information has real physical consequences. Erasing or processing data literally takes an energetic toll. But while physics elegantly proves that information has a thermodynamic cost, thermodynamics absolutely cannot explain where meaningful semantic sequences actually come from. It's kind of like thermodynamics describes the energy constraints of the hardware, but it tells us nothing about the origin of the software. And this is exactly where the current philosophical debate sits. Impartially speaking, the intelligent design perspective actually agrees with standard physics here. They aren't making that scientifically inaccurate claim that entropy disproves evolution. Instead, they're asking a much more targeted question. Yes, physics allows for complexity, but do unguided energy flows and blind mechanisms possess sufficient causal power to actually write semantic, functional code? It's a lot to wrap your head around, right? I mean, here we are, we exist as conscious beings, packed full of impossibly intricate molecular machines, actively thinking and learning in a universe that is just steadily decaying toward thermodynamic equilibrium. The laws of physics are undeniably operating all around us, constraining and directing the cosmos. But it leaves us with this profound realization and a massive question. Does physics alone tell the full story of how all this meaning and encoded information came to be? I'm going to leave you to ponder that incredible question. Thanks for joining me for this explainer, and I'll catch you next time.